Children, let us now talk about the factors affecting resistance. We know that resistance is the property of a conductor to resist the flow of charges. To study the factors, we have here a simple circuit consisting of a cell and a meter and a key. A nichrome wire of length L and area of cross-section A is connected across the points A and B. The current flowing in the circuit is noted and the experiment is repeated with different cases. In case 1, a nichrome wire of length L and area of cross-section is connected across the points A and B. Here we note the value of current, let it be I. In the second step or case 2, a nichrome wire of length 2L, that is twice the length of the previous wire, is taken and the thickness or the area of cross-section is taken as A. It is connected across A and B. The first wire is replaced and in that place we are keeping this wire. So what do we see? We see that the value of current is decreased to half of its initial value. Why is it so? It is due to the increase in the resistance offered by the circuit. As the length of the conductor or the wire increased, the resistance also increased, that led to the decrease in the value of current. In the third case, a nichrome wire of length L and thickness or area of cross-section 2A, that is twice, is connected across A and B. So what do we find in this case? We find that the current is doubled. It can be clearly understood because as the thickness is increased, the electrons get more space to move, and as a result, the hindrance or the opposition will be less. Or we can say that resistance is inversely proportional to the area of cross-section of the conductor. In the last step, or in case 4, we take another wire, a copper wire of length L and area of cross-section A, and that is connected across A and B, and there we note the value of current. We get another value of current. In the previous slide, we discussed about the factors affecting resistance. The resistance of a conductor depends on length of the conductor, that is R is proportional to L. More is the length of the conductor, more is the resistance, and vice versa. It depends on area of cross-section of the conductor or thickness of the conductor, that is R is inversely proportional to area of cross-section. That means higher is the thickness of a conductor, less is the resistance offered by it, and vice versa. Third, it depends on the nature of material of the conductor. The resistance offered by different materials are different. Also, it depends on temperature. Thus, by using the first and the second factor, that is R is directly proportional to length and R is inversely proportional to area of cross-section, if we combine these two, we get R is proportional to L by A, or R is equal to constant into L by A, or R is equal to rho L by A, where rho is called the electrical resistivity of the material of the conductor. Electrical resistivity noted by the letter rho. In the previous slide, we introduced a new term or a constant named electrical resistivity, and we formed an equation to calculate resistance, that was R is equal to rho L by A. If we rearrange that equation, we can get an equation to calculate resistivity. Rho is equal to RA by L. So we have to define resistivity. If we take a conductor of unit length and unit area of cross section and we put the values in this particular equation, we get rho is equal to R. Or we can say that resistivity of the material of the conductor is defined as the resistance of that conductor having unit length and unit area of cross section. That means resistivity is the characteristic property of a material. It doesn't change with the length or the area of cross section because it is limited to smaller dimensions. Suppose we compress a material or we stretch a material, the resistance of the material change, but it has nothing to do with resistivity. The SI unit of resistivity is ohm meter. Resistivity changes only with temperature and with the nature of the material. Different materials have different resistivity. The metals and alloys have low resistivities, hence they are good conductors of electricity. The insulators like rubber and glass have high value of resistivities. The resistivity of an alloy is generally higher than that of pure metals, but their resistivity changes less rapidly with the change in temperature. For these reasons, they are commonly used in heating devices. Tungsten is used for making filaments of incandescent lamp due to their high resistivity and high melting point. Thank you.